Okay, so let's look at the first question of tutorial 3. We're asked for 0.5 mole of an ideal gas at 20 degrees Celsius is allowed to expand isothermally against a constant pressure of 2 atmosphere, and we're given the initial and final volumes, and then we're asked to calculate the entropy change of the system, the surroundings, and the total entropy change. And we're also asked to explain whether or not this process is spontaneous or not. Right, so what do we first need to analyze what we're asked. Okay, so I'd like to start with what we're asked to do. So in other words, looking at this section here. So looking at, where's my highlighter? It's my highlighter. At this little section here. So we see that delta S total, recall the delta S total will be equal to the sum of delta S system plus delta S surroundings, right? So that's how we calculate that. So in other words, once we have those two quantities, then we'll be able to calculate the total entropy change. So that means we also need to calculate those two independently. So the change for the surroundings is of course always, because it is whether or not it's an irreversible or a reversible change, doesn't really matter because it's a state function. It will always just be dependable or dependent on dependent on the heat of the surroundings. In other words, the heat given off or taken from the surroundings. So it will be dependent on that. So we need to calculate. In other words, we need the heat. So we know it's at a constant temperature. So that's great because we're given the temperature. So we already know that. And then delta S system. We have one or two equations, right? So we know it's either nR ln Vf over Vi, or it can be NC Vm ln Tf over Ti. Right, so it's either one of those two, but we can immediately eliminate this one. Why? I mean, because it's an isothermal expansion process. So there's two things here. There's no change in the temperature, so in other words, that's irrelevant, and also it's an expansion process, so we can't use the constant volume heat capacity. Anyway, so those are two things that should give you an indication. Even though, I mean, the second one, you can use the constant pressure heat capacity, but okay, anyway. But it's an isothermal process, so there's no heating involved because that expression is used normally for heating. So you wouldn't be using that. You would be using the one for the expansion process because we're given two volume values. We're expanding. It literally says we expand something isothermally from one at a constant pressure from 1 liter to 5 liter. Sometimes I think students don't really read the question. I mean, it says we're expanding something isothermally, so you need to see what is actually happening to this gas. You know, you have a gas in a cylinder and it is being expanded. You know, see what's happening and it will help you analyze the question correctly. All right, okay, and then we just basically have to find a way to calculate these. So let's start with the one where we have immediately everything that we need, so meaning the entropy of the system, because I mean we're given everything here. So the entropy change of the system is nR ln Vf over Vi. Then, so I mean that's 0.5 mole. R is 8.314 joule per Kelvin per mole. 3145 mole, whatever. You can use whatever one you want. That last digit doesn't really make too much of a difference. 5.5 liters, the final value, and the initial value is 1 liter. And then we get 6.7 joule per Kelvin, right? Because the moles cancel, and then we're just left with joule per Kelvin. Oops, joule per Kelvin. Okay, so that's our system change. And remember, this will be the same for a reversible or an irreversible process. Why? Because entropy is a state function, so it doesn't matter what the path is, it's path independent. So, vibes. All right. Okay, so moving on to the surroundings change in entropy. So let's just rewrite this here. We need to look at the heat of the surroundings. So basically the only way we can calculate the heat is we're looking at the only equation that we have for heat, and that involves the internal energy. So that's heat plus work. Right. And we're also given the fact that the change is done isothermally. So in other words, we know that the change in temperature is 0. So in other words, we know that the change in internal energy is equal to 0. So that means that our change in our heat, or heat, is equal to negative our work. But that is for our system, right? So let me just make a little sort of just like a little subnote that is for our system. So the system's work is, the system's heat is negative the work done by the system. Okay, so let's calculate the work done by the system. Of course, it's an irreversible process, so that's equal to P external delta V. We're given P external, it's 2 atmospheres. Also given delta V, it's 5 minus 1 liter, so that's 4 liter. And of course, we can convert atmosphere to kilopascals and liter to cubic meter. But we can also use, there's a nice conversion factor given in your textbook, which is 101.3 joule per liter atmosphere. So if you ever have any calculations which involve liter and atmosphere, then you can quickly convert to joule using that. So this gives us a value of minus 810 joule. Okay, so that means that our heat of our system is equal to 810 joule. So that means our system needs to absorb 810 joule from the surroundings to keep this process isothermal, right? Because that's technically what this up here implies. Because this process is isothermal, it means there needs to be a balance in the energy between, or the energy that does. So the system does work, and that then needs to be balanced by the heat brought in from the outside. So in other words, where does the system get the heat from to do the work with? It gets it from the surroundings. So that implies that our surroundings heat is again negative this 810 joule. Right, so that's a very important distinction that you need to make for yourself. So in other words, the change in our surrounding entropy, or surroundings entropy, is then equal to minus 810 joule over the constant temperature that everything's being held at, which is 293.15 Kelvin, which then gives us a value of minus 2.8. Now we have joule divided by Kelvin, so it's joule per Kelvin. Right. So then in the end, we can have our total entropy, which is equal to that 6.7 that we had for the system, 6.7 minus the 2.8 we have here, which is equal to 3.9 joule per Kelvin. And that's of course larger than 0, so that means the process is spontaneous. Right. And just some more interpretation in terms of that. All the information that we're given initially gives us, so we're initially given, if we look at the initial parameters, we're given that the initial temperature, because it's isothermal, it's 293.15 Kelvin. We're given the initial volume is equal to 1 liter. Yeah, 1 liter. So we can quickly calculate the pressure, right? The pressure is equal to nRT over V, and that works out at 12 atmosphere. And if we think that P external is equal to 2 atmosphere, 2.0 atmosphere, that means that our P is much larger than our P external. Therefore, it makes sense that it will be spontaneous. Right, because you have a gas with the piston in here, and we have here 12 atmosphere pressing. Now let me just use a different color. Let me use red. Pressing up against only 2 atmosphere. So which way will the piston move? The piston will of course move against the 2 atmosphere because there's not enough force pushing down against the 2 atmosphere. So against the 12 atmosphere. So the 12 atmosphere will drive away the piston quite easily, and that's why it's spontaneous. And I mean, it makes sense from all the calculations. So that's why I've always said, these like little diagrams, they might seem very stupid to you, but they're quite useful. They're very nice to just give you a very quick idea of what's happening, and so that you can think about what's actually going on in the system that you're calculating. Right. Okay. So even though it's a very simple question, there's a lot of interpretation, there's a lot of niceties going on in it. So I hope this was useful and that you enjoyed your first tutorial question.